And Franzke. And you should all know Christian. He was, of course, in Hamburg for a long time. He also started his career in Hamburg with doing thesis in those days with Klaus Friedrich. And then he went. He also did his PhD here with Klaus Friedrich, and then but then he went away to Courant Institute, I think, in New York, and also to NCAR in Boulder, some other places. But then finally you arrived here again, working with us as a senior scientist. And finally, Christian went then to Pusan National University, which is in Korea, South Korea. And he's working there at the research center, or climate research center, which is newly founded recently. And Christian is a very productive scientist. I think with scientific publications now as first author, and on a variety of topics, right? Parameterizations. The workshop you gave today or last 3 days was on stochastic parameterization and stochastics in general. So lots of stochastics work, but also work on energy. And this is what Christian is presenting today: potential energy.
Thank you very much, Carsten, for the kind introduction, and also thank you to the TRR for having me come here, for giving this short course and now a seminar. So I'm going to talk about some work we are doing, or I'm doing here with Chen Liu. He did most of the work, actually, also with collaboration with Valerio Lembo, which probably is also still known here. He was also postdoc during the first phase of the TRR. Lenka Novak from Caltech and Rémi Tailleur from University of Reading. So we're going to look at some energetics framework for understanding large-scale circulation dynamics and changes, and especially we try to do this from a local energetics perspective. That's a brief outline of what I'm going to talk about. The very famous Lorenz Energy Cycle, but that's something basically a globally integrated view, because then computing the so-called available potential energy becomes relatively straightforward, which is more problematic if you want to do this from a local perspective. After reviewing the Lorenz Energy Cycle, I go into local energetics, especially how to compute a local version of the available potential energy, and then I briefly show some recent results. So it's, currently in the process of writing up a paper, but there's still some, maybe just some outlines what we might want to do in the future. Lights are hanging. Oh. No, sorry about this. Let's see just a few or some figures of the large-scale circulation from different points of view. Here we just look at the 200 hectopascal wind fields in a climatological view. So we have here the jet streams over the North Atlantic and here the North Pacific. So that's a mean view. But if you look at kinetic energy, so that's basically where we look at fluctuations, of course, and also climatologically averaged. And we also see basically where we have strong mean winds, we also have strong fluctuations. So basically that's where we have lots of kinetic energy. And here we look at low frequency. Why we do this becomes clearer later. So basically we will then decompose our energy budget into low frequency and high frequency energy. So that's, and we can see here in the solar mean, so we have here the latitudes, vertical levels on this side in hectopascal, and most of the kinetic energy is concentrated here in those jet stream areas at about 200-300 hectopascal height. And here maybe I should mention this, that's also vertically integrated. So that's already very interesting. I think that where we have the strongest fluctuations, it's also where the mean winds are strongest. So if we look in the causes of atmospheric fluid motions, then what the major source is, of course, diabatic heating. And it actually turns out it's basically not just having diabatic heating, but that we also have some gradients of diabatic heating. So especially the horizontal heating gradients is very important. So if we assume we would have a stably stratified atmosphere, then about 98% of all the atmospheric kinetic energy would basically due to those horizontal heating gradients. And it's only a very small part, say the remainder 2%, which is due to convection, basically a vertical gradient of diabatic heating. So that means that especially the meridional temperature gradients are very important. And also if you then look here at some simple box, where we basically separate this, we have here cold air, warm air. So one could imagine here we have the equator. So we have lots of solar radiation coming in. So that's heating the atmosphere. Here we have the polar regions where we have lots of loss of heat and radiation to the space. So then we can have here basically see this with the temperature gradient, and here we would have the center of gravity. If we now would remove the separator here so that we have basically some kind of redistribution of warm and cold air masses, then basically we would have the heavier, the cold air goes to the ground and warmer air basically rises up. So that also means that the center of gravity gets lowered down. So basically there we have a release of potential energy into kinetic energy. So basically it's this behavior which basically creates the conditions that we can actually have or motions, kinetic production of kinetic energy. And that's also, of course, very important if you look at individual storms and say that the magnitude of storms are also typically measured in terms of kinetic energy, because it's then also proportional, say, to the damages they might cause to buildings or forests. So that's also one reason why it's very important that we look at kinetic, the energy budget in the atmosphere. And also if we characterize intensifying or weakening storm systems, then we typically also say that they're gaining or losing kinetic energy, and basically can also look at the energetics of those storm systems. So if we would only consider adiabatic motion, then the total energy of the whole atmosphere basically would be constant, and the only sources or things for kinetic energy would be basically potential energy or the internal energy of the atmosphere. So it's basically those non-adiabatic processes, so including latent heating, radiative heating, but they directly only alter the internal energy. But that means also to the first order, we might not really have to explicitly include moisture effects, say latent heating. Something which we would like to do in the next step, but of course then the whole formulation would become somewhat more complicated, but that's aimed to also understand how global warming, more moisture in the atmosphere would then actually affect circulation, atmospheric circulations and the energetics. But right now, we kind of use a try formulation and just motivate this that latent heating would actually only directly affect the internal energy. And then the total potential energy, that's basically the sum of the potential energy and the internal energies, and this ratio, potential energy P, internal energy I, this is actually constant if we have a hydrostatic equilibrium. Also some constraint on the energetics, but actually the total potential energy is not really a good measure for the amount of energy available for conversion to kinetic energy. Because if we go back to our simple box, then basically the center of gravity basically can't really sink down to the surface. Only then we basically would convert all the potential energy into kinetic energy. So there is only a certain fraction of the potential energy available for conversion into kinetic energy. So that's so-called available potential energy. And how do we estimate this from observation or model data? So we basically look at the difference between the actual atmospheric state and the adiabatically rearranged reference state. And this reference state is basically the stratification, both horizontal and statically stable. And the minimum total potential energy would correspond to the maximum kinetic energy, which we basically can convert.
So can you explain what adiabatic rearrangement means?
So in case that the actual atmosphere wouldn't be stably stratified, so you just take your air passes and rearrange them so that basically you would have a stably stratified atmosphere.
Like this in the figure with no gradients, no horizontal gradients.
Yeah.
And what is adiabatic? Means no change in the temperature of the fluid element, or what is adiabatic?
So basically, your air passes wouldn't exchange heat with the environment. So if you change it to a different pressure level, then that might then change the temperature.
Yes, about moisture.
Right now, we ignore the effects of moisture. Or because that would make the definition more complicated. Any other questions? Okay, so basically we rearrange those air passes and then we integrate over the whole atmosphere. So that's basically how Lorenz basically developed the Lorenz Energy Cycle. So if we now look at how to actually compute this and practice, so the exact available potential energy derived by Lorenz is this expression. So basically we look at, instead of pressure levels, we look at levels of potential temperature. Then we basically look at those pressure differences. Those overbars are either isentropic means, or if we go to QG approximation, isobaric means. So basically we average over those pressure levels. The prime quantities are perturbations from the global mean. And then we have here also this gamma, that's basically the lapse rate. So that's the exact formulation, but typically most Lorenz Energy Cycle software packages basically prefer to do this on pressure levels. For this, you have to use the QG approximation. So you get this expression here, which you can then also simplify to this expression here. So you look at the temperature, the spatial deviations, or we call this the spatial variance of the temperature with respect to our reference state, which would be a horizontal mean, which can then, of course, vertically change. And of course, here the difference in the averaged lapse rate versus the local lapse rate. So if we now just plug in here some reasonable numbers, which you can see here. Then about less than 1% of the total potential energy is actually available for conversion into kinetic energy.
In the uppermost line, the basic state is also only a function of Z or pressure or whatever.
Yes.
No horizontal change.
We integrate basically over the, you're on one isentrope, and then we integrate over this isentrope. The Lorenz energy cycle is always more like a global view of energetics. That's what we do next. But the Lorenz energy cycle is only a global point of view. Because locally you have to look, or it becomes more involved to calculate APE.
She would do this local, she still calls it Lorenz Energy Cycle.
Yes,
Maybe just cement.
But I will show you in a couple of slides that actually if the way you compute this actually might show you large deviations for APE, depending on how you compute this.
The point is the state of minimal potential energy the same as the reference state which you have there in the uppermost line?
Yes. That's basically the aim, that you rearrange it in that way. Because then, I mean, that's the potential energy which is available for conversion into kinetic energy.
Yeah,
but of course, still doesn't mean that all of this will be converted.
You can rearrange, or you can do this integral over pressure levels.
Yeah. Well, here you make an approximation, so it's not exactly the same.
Yeah.
And I'm going to show you later that it's actually not such a good approximation.
But before you do this approximation, that would be the same. Yeah.
That's the exact expression. Or what is the same to what? You asked me whether this is the same to this line or to something else.
No, there. First you said you rearrange your parcels.
Yeah.
And here in this uppermost line, you say that the reference state is integral over pressure levels.
Well, that's then the APE. We then integrate over those isentropes.
Yeah, but that's the same thing as rearrangement of parcels, which is a non-local operation. We're involved, and this integration over the pressure levels is the same thing. Mostly because this is the problem in ocean, because it's not obvious that the horizontal integral is the same thing as this rearrangement of parcels and finding the minimum potential energy.
Yes, it's not exactly the same. I mean, that's 3 or 4 slides. I will show you that depending on how you compute this, with which also rearrangement method, you might get slightly different or large differences. Okay. So what are the sources and sinks of available potential energy? So basically, if we call here increase in spatial temperature variance, basically if we would have increase in meridional or horizontal temperature gradients, or if we then have reduction in sensible or latent heat release, or cooling in the upper troposphere also, this stabilizes the atmosphere, so that would be sources of APE. Or if we then have rising warm air undergoing adiabatic cooling or sinking, that would actually reduce those temperature gradients. And then, of course, heat transport, upward heat transport increases stability, so that would be a sink of APE. So we can look then also at the kinetic energy. That's, of course, very straightforward to formulate this locally. But again, we, of course, integrate here globally, and then basically one can write down a tendency equation for APE, and one for the kinetic energy, and one can see that there's of course those conversion terms. And they also have the opposite sign, and then we have here generation terms for APE and KE dissipation terms. And under adiabatic frictionless flow, then basically those generation dissipation terms vanish, and basically the energy or the sum of APE and KE is conserved. Then we can do this typically Lorenz energy cycle. We look at the solar mean state, and then basically what's called here eddy deviations from the solar mean. So we can define those quantities here, and then also get the tendency equations, and we also again see here those conversion terms between the different quantities here. Then one can look into more detail what actually causes here temperature variance changes. It's to production of APE, wind variance changes, basically leads to the conversions between eddy and solar kinetic energies. And if we have here changes in solely average temperature and wind changes, then we can get conversions from potential energy into kinetic, and the same here for the eddy terms. And then one can look at those diagrams characterizing the Lorenz energy cycle and just look how strong the energy reservoirs are for those 4 different quantities and also the conversion terms. But then already here that they look also at 2 different data sets, NCEP reanalysis era, I think that's probably era 40 reanalysis, and you can already see there are some differences in those estimates. And those numbers here, that also already indicates that the differences, they are on the order of 10 to 20%. So which is, of course, quite a large uncertainty if one looks at the global energy budget. Then one interesting question is, of course, how this might change in the future. But here, or maybe first in the past, do we see trends? And yeah, we see trends in certain quantities. Here also comparison between NCEP and era interim. And basically, oops, why this doesn't work very well. And overall, basically, efficiency of the Earth's global atmosphere as the heat engine increases. So we basically get more energy conversion. And here, APE and Caldera, that they looked how this might actually change in a warmer climate. So they have experiments 5 times CO2 compressed with 4 times CO2. And they see basically that the APE actually goes down a bit. And basically also they relate this that the major temperature gradient might change. So in global warming simulations, at the surface, we have an increase in the polar regions, here DJF, but at the same time, in the upper atmosphere, we have an increase in temperature over the tropics. So basically, we get here the opposite gradient in the upper troposphere than we have here in the lower troposphere. So we have some kind of competing effects. And so now it's the question, how important this actually would be, or which of those 2 effects would basically win in order to explain, or which circulation changes we can then actually explain or expect due to this warming climate.
These results are contradicting each other, that the production terms are increasing, but the energy level of APE is decreasing.
In the local framework, we see that actually locally there is also increase in APE. Whereas most other regions, but I will get to this, there we don't see that's such a strong change.
In the global, on the left panels, there were global energy transfers from the energy production of APE.
Yeah.
And this is increasing.
The conversion, yes.
More, but there's less APE. That's a contradiction.
maybe more APE, even though APE might go down more, maybe more might be available for conversions into kinetic energy. That's
relation between production and the energy level itself.
And you could imagine if you rearrange the atmosphere due to global warming, that maybe there might be more conversions from APE, even so APE might go down. I mean, that's also, we also see some contradictions between the Lorenz formula. If you look at trends, what we can expect from the Lorenz formulation with the QG approximation and from the local framework, so that they also might show changes in opposite directions. That's still something we might have to look more closely into it. Okay, now local energetics. So how do we actually define local APE? So we first define the frequency forces that act on each parcel between its actual level and the reference level. So basically there is work necessary to bring a parcel from its reference state to its actual state. So that's basically expressed by this expression here. Alpha, that's basically 1 over the density. That's always positive. And the reference state, we define this basically as the level of neutral buoyancy. So it's basically, that's the level where basically the pressure at which the reference potential temperature is equal to the potential temperature of that parcel. So that's basically our criterion how we want to redistribute all those air passes. That we basically get to this state where basically the parcel, this pressure where basically the reference potential temperature is equal to the air parcel potential temperature state. So there are different algorithms for doing this. There is the so-called parcel sorting algorithm. So for each time, the global potential temperature is divided into those parcels, and then we just try to typically one has to then implement some efficient sorting algorithm to basically efficiently rearrange the parcels. More simpler, faster is probably this latitude-weighted isobaric average. If you look at those two schemes, so that they actually look, maybe here at the surface, they show some difference, but after odds, then if you go up in the atmosphere, they actually perform relatively similar. So that's.
Sorry, is this the same as averaging temperature along isobars horizontally, as you said at the beginning?
Yes, but it's really weighed by the latitude this time.
But the most precise one would be the first one, passes one.
What isentrope? Or you mean here locally? Yes, but it's computationally more expensive. So okay. That's an important graph here. So here we compared the exact Lorenz APE with the APE from those different approaches. So the dashed line, that's basically the 1-1 line. So basically, if the closer those points are to the dashed lines, the better, or the closer they are to the Lorenz APE, to the exact Lorenz APE on isentropes. You can see the QG approximation of the Lorenz formulation that basically performs worst on pressure levels. If we then go here to the local formulations, it's basically those blue dots and the grape dots, especially this the quick sort algorithm performs best, or there we get, if we then take the local formulation and globally integrate, we get very close to the exact Lorenz APE formulation. And then Lorenz QG on potential temperature levels also performs much better than on pressure levels. So that already indicates that the way we compute APE seems to be also very important for the accuracy. So now one could, of course, like in the Lorenz framework, look at the zone mean and deviations from the zone mean and call this the eddies, but of course for certain applications it might be more or better preferable if one has a different definition of the mean state. And here we look or define the mean state as the low frequency fluctuations, which would then also include the climatological mean versus high frequency. And here basically we take the 10-day fluctuation cut off using some non-just filter. Okay. Now we can basically compute the mean or the low frequency APE and the high frequency or eddy APE, and then can look at those tendency equations. And those equations now, because they're local, they not only contain those conversion terms we know from the Lorenz Energy Cycle, but also some advection terms here. So we also split it up into mean advection, eddy advection. That's here for what we call the mean or the low frequency flow, and here for the high frequency flow. And then here we again have those conversion terms, and also diabatic heating terms formulate here. But then we can do the same for the local kinetic energy. And then also again, we get here the conversion terms, which are in colors, and then also lots of advection terms or some other terms due to the formulation that we are on a sphere. But they just lead to redistribution of energy and are not really energy things or sources. So if we would globally integrate those equations, then they would actually drop out, and we would only keep those conversions. Okay, now looking at the spatial distribution of those, here the APE, low frequency, high frequency, and kinetic energy. So here again, that's vertically integrated, and here we see the zone mean of figures. So here the low frequency APE is located mainly in the polar regions or very high latitudes, whereas the high frequencies are more in the mid latitudes where we would expect storm tracks and jet streams. You can also see this here in the zone mean view. Also, that's also mainly say in the mid to upper troposphere concentrated, and similar for the kinetic energy. Whereas maybe here also the high and the low frequencies are probably more located in the mid latitudes, and also similar here in the zone mean view. But if you look at APE a little bit more in detail, so for the low frequency, we see the maximum in upper level of high latitudes. Second maxima is also here over the tropics, but it's of course much smaller amplitude than over here the high latitudes. And that also resembles the temperature pattern over the continents.
State here. I didn't get what mean state was used.
That's just all fluctuations with periods of more than 10 days.
No, I mean
that's what we call mean state. We don't take a climatological mean.
I mean for the APE definition, parcel sorting or version, which version?
That's the parcel sorting, the best one. You mean in the spatial distribution? I can't remember whether we've done this or not. I think we probably decided here that we use the parcel sorting method and moved on. But it's a good question. I will look into this once I'm back. And for the high frequencies, then we have the maximum where we have the storm tracks over North and North Pacific, North Atlantic. Also here stands from 500 to 200 hectopascals. And also here over the southern hemisphere. That's of course not very surprising, similar to the kinetic energy, so it's very closely related to the jet stream storm tracks. And also they say some, especially in the northern hemisphere, that we have the subtropical jet and the eddy-driven jet, so that's kind of here a little bit smeared out, this distribution. Then we can look at those local terms, conversion terms, or diffraction terms. They have those structures here. And that's basically dominated also by the mean advection and the diabatic heating, the forcing. And that's basically, and the diabatic heating is kind of compensated by here the conversion into eddy kinetic energy. And the mean advection is basically the only term where you have positive values at the start of the storm. So that means this mean advection of the APE is actually important for the initiation of storms and storm tracks and the maintenance of the storm tracks, which we then also nicely see here. It's here the high frequency budget of APE. So on a global scale, that's dominated by those conversion terms, forward often at the location of the storm tracks here. And these affect the total APE density to the equator-ward flank of the storm tracks, and a small amount of the eddy APE density is affected by the mean flow further downstream. And also a small amount is then generated by sensible and latent heating from pre-existing eddies within the storm tracks. We can look at the high-frequency kinetic energy budget terms. Again, on a global scale, dominated by those conversion terms and the dissipation. At the locations of the storm tracks, at these affect the total APE density, and this conversions between APE and kinetic energy is basically compensated by the low frequency eddy advection of the high frequency temperature anomaly in the middle atmosphere if one looks at this in more detail. And then the low frequency kinetic energy budget is dominated by this conversions between APE and kinetic energy and the dissipation again. And the advection basically leads to further downstream development of the jet stream. This conversions here between the high and low frequency kinetic energy peaks at the downstream end of the jet streams or storm tracks where the occlusion of the disturbances occur. So, and there we would then infer that the barotropic processes should be very important. So looking at the budget, it's of course always important how well our budget is actually closed. We look here at the low frequency APE. So that's the local tendency. So that would be the left-hand side. And then we can look at the sum of all terms on the right-hand side. So that's what we call here the residual. And that's basically, you can see that they actually closely correspond to each other. So there's here our Siberia or East Asia, so probably the largest amplitude, but it's also here, I don't know, about troposphere, probably already lower stratosphere, where we might have some deviations, but that's also already the highest vertical level we consider. So maybe that's also due to some numerical problems with the boundary condition here. But that's kind of very well balanced. Also, if we would look at the other quantities, high frequency, APE or kinetic energy, they're all very well balanced, which is very good. And also here we looked at the diabatic heating. So we can compute this ourselves from the temperature tendency from the ERA 5 data. So that would be the structure of diabatic heating. Here the solar mean, or we take what we can get from ERA 5 directly from their tendency. You can see here very close correspondence. So here and here we just computed the difference, but also here of course not perfect, but also this is very well, compares very well. So the way we compute in our budget this diabatic heating is actually very closely to what the model or the direct model output of diabatic heating terms produces, which is also of course very good. Okay, now just briefly talking about some applications, what we can do with this, trying to understand or looking more into jet stream shifts. So there is, of course, in the literature, lots of papers reporting on a forward shift of jet streams. That's basically indicated here. So we look at long-term trends in the winter season. The contour lines, that's the climatological structure of the jet stream of solar mean wind. And then we can look here at the trends, which would be here the color coded here. And we can see there is some poleward shift of the jet stream over the North Pacific, also here over the North Atlantic. And then we can, of course, look at different quantities which are related to kinetic energy, just looking at U squared or the column integrated U squared, column integrated KE, to see which terms actually contribute most to this. Also here the vertical wind, and it's of course the change in the solar wind, which seems to be much more important in explaining the change in kinetic energy than the changes in radial wind. And what I already mentioned in the beginning, what we now also try to understand more, but that's the work we have to do, is basically looking at the differences between what's happening at the surface when we have warming basically in the polar regions versus in the upper troposphere where we have the warming mainly in the tropics. So that's of course what either we would argue you might have less meridional temperature gradients, or you would have less buckling instability, or you might actually have more if we look at this more at the upper troposphere. So, Arctic amplification, maybe you would argue should be more like a quarter-watt shift, that stream upper tropospheric warming, then that might implicate more on northward shift. Then we also started looking at long-term trends of those energy terms. And say if we look at the low frequency APE, then we see, especially here, an increase over Siberia, or Northeast Asia. And also the location where we see, say, in our residual, the largest area. So maybe that also might be just related to this trend behavior. Then over to the polar regions or the Arctic regions, we see some decrease of APE. So we still try to understand this. Then we can also see here that the high frequency APE is probably more in locations of the trends are more where we have the jet stream storm track, so there we might have some, or can expect that this might explain some of the observed changes, and also the kinetic energies seem to be related mainly to changes in the storm track jet stream. So those long-term trends, so now we looked at the budget terms or conversion terms, and our current conclusion is that mainly the mean advection causes this accumulation or this trend here in low frequency APE. And changes in this conversions between high frequency, low frequency APE is kind of compensated by the diabatic heating, or diabatic heating changes would then lead to conversion terms here, or increase in the conversion here. But then here our conclusion is we look mainly here at the comparison between those fields. Another topic we have started looking in is also looking at individual storms. Here we look at a couple of the most intense storms in the North Atlantic region. Here we just have a list of 5 of the past, the 5 most intense storms. And there we hear first just the evolution of surface geopotential height. So you can see how the storm moves over those 4 days, and of course also how the wind speed changes. Now we wanted to see whether we can explain this with kinetic energy changes or the energy budget changes. So we can look here at the low frequency changes, but of course low frequency, not that much changes. And then here the high frequency eddy, the kinetic energy changes, but there is actually not that much of a close correspondence to say changes in the wind speed. And we actually expected wind speed would be relatively fast quantity, so this actually should show up here in the high frequency eddy kinetic energy, but that's not the case. So that made us thinking, and it's actually this interaction between the low and the high frequencies which are important for the storm development, which I found a little bit surprising, but of course it's then this energy, this cross-frequency energy transfer, which seems to be very important in those storm developments. That's something we want to look more into the future. Maybe I just come here to my summary. So the Lorenz, he was the first coming up with a global view of the energy budget. So he defined APE, but most studies basically don't use the exact formulation from Lorenz APE. They use this QG approximation on pressure levels. But this is not, as I showed you, not a very accurate approximation. So here, Lorenz also provides a global view of the energetic. Here we provide the local APE definition so that we can have a local view of the kinetic or the energy budget. So that's both relatively exact or close to Lorenz exact formulation. It's also still relatively easily computable. That's also very good if we want to compute APE locally. And the APE basically depends on the departures from the isobaric mean, depending on the formulation. Now we are actually able to come up with a local formulation of the whole energy cycle, which I showed you in some examples, what we did and what we might be able to explain in the future, storm tracks and maybe changes in the circulation. Okay, thank you very much for your attention, and I'm happy to answer your questions.
talk, Christian?
I have one. Can you please explain the difference between convective available potential energy and the local APE? How are the two different?
Convective available.
Yes.
I mean, there, of course, the air part, I mean, you need to for convection to start, basically, you need to get across basically the what's called the level of inhibition.
Right.
And basically, then the air particle could rise up to the level of neutral buoyancy. And it's basically this difference
Yes.
between those two levels, which is basically the convectively available potential energy. Here in our APE,